To understand modern AI, look at the default state of a large language model. At its core, it is a pure text processing engine. You give it a prompt, it returns a block of text, and the interaction ends there. It is mathematically incapable of reaching out and interacting with the real world. These systems are auto-regressive. Their entire architecture is dedicated to one highly specialized function, calculating probability distributions to predict what the next word in a sequence should be. This diagram shows that prediction process in real time. The model evaluates a list of probabilities and selects a single token to continue the string. But this creates an inherent limit. An isolated model has no persistent state between prompts, no memory of past actions, and zero independent agency. So the engineering challenge becomes clear. How do we take a static, frozen text model and architect it into an autonomous entity? In computer science, an agent is strictly defined as an entity that perceives its environment through sensors, maintains an internal state, and executes physical or digital operations via actuators and APIs. Achieving this level of autonomy does not require rebuilding the foundational transformer architecture. The weights of the model can remain completely unchanged. This behavior relies on a structural shift in how we handle the input sequence. By weaving environmental observations and internal states directly into the text string, we can redirect the model's core prediction objective toward the active management of a goal-oriented trajectory. To see why this sequential method works, we first need to look at how dialogue systems were historically built. In 1966, Joseph Weizenbaum created ELIZA, an early conversational program that relied entirely on hard-coded templates and rule-based logic to simulate an ongoing state. ELIZA worked as scanning user inputs for specific words and assigning them fixed priority ranks. It then matched those words against a list of pre-written patterns. If a user deviated from those exact keyword configurations, the entire conversational illusion broke down. This brittle approach eventually evolved into the standard dialogue state architecture. This diagram shows a highly modular pipeline where speech is converted to text, semantic meaning is extracted, and then passed to a centralized state tracker. The dialogue state tracking module is responsible for maintaining the system's current belief of what the user wants. It stores extracted variables, like a request for a cheap hotel, in a rigid JSON object. A separate dialogue policy module then reads that JSON state and uses it to deterministically select the next pre-programmed system action, such as asking the user which neighborhood they prefer. The bottleneck here is the requirement for massive amounts of direct supervision data. Engineers had to manually label and map every single valid state and acceptable action to train the individual modules. While this pipeline guarantees specific outputs, its rigid modularity makes it impossible to scale. It cannot handle the unbounded, unpredictable nature of a long, multi-turn conversation. Modern LLM agents move away from modular pipelines by framing dialogue state tracking and policy selection as a unified token prediction task. This input diagram illustrates the serialization process. The dialogue history, the current state variables, and the system actions are all concatenated into one long string of text. To keep the model from confusing user dialogue with system data, developers use strict formatting delimiters. Tags like angle brackets enclose the exact domain and price constraints directly inside the string. Because the state is mapped out in text, the LLM can predict a necessary system action using the exact same next word logic it uses to generate a normal sentence. Once the model predicts a required action, like querying a database, generation pauses. The database executes the search, and the results are programmatically injected straight back into the prompt sequence. The LLM then resumes token prediction, generating a delexicalized response. It writes a generic sentence structure with placeholders, which are immediately filled by the specific names and numbers pulled from the database query. By serializing everything into a single text document, the entire architecture eliminates the need for separate tracking modules. The model relies on its vast contextual memory to manage the conversational state natively, but serialization alone only solves conversational tracking. The internal weights of an LLM represent a frozen snapshot of training data, meaning it still cannot access real-time information or perform precise mathematical calculations. To grant the agent capacity beyond its training data, developers integrate external APIs. They do this by training the model to output a specific syntax, the tool name, the required parameters, and a placeholder for the result. This execution trace shows the model writing a sentence, recognizing a gap in its knowledge, and generating a specific query code. Generation halts entirely while the external search API runs. Accessing APIs requires high-level planning. The API returns the answer, appends it into the brackets, and the LLM resumes generating. The probabilities for the next tokens recalculate based on this newly injected real-world context. The model can now discuss the Massachusetts Medical Society with complete factual accuracy, grounded in an active external query rather than its static memory. Models learn to do this through a methodology like Toolformer. During training, the system iteratively samples thousands of candidate API calls. It keeps only the specific tool calls that demonstrably lower the loss or error rate of its future token predictions. By internalizing API syntax as specialized tokens, the LLM graduates from a closed loop of generation into an entity that interacts with live software environments. Accessing APIs requires high-level planning. This equation represents the expansion of an agent's capability, combining standard executable actions with internal thoughts, creating an expanded action space necessary for solving complex, multi-step problems. To see why this expansion is necessary, we can look at a standard hotspot QA task, asking what other device can control the program the Apple remote was originally designed for. Under standard prompting, an LLM attempts to guess the answer directly and fails. If we use a chain of thought prompt, the model tries to reason step by step. It associates the remote with the Apple TV and deduces that iPhones and iPads are the answer. This logic breaks down the problem correctly, but the premise is factually wrong. Chain of thought frequently results in hallucinations because the model lacks any mechanism to verify its assumptions against external reality mid-sequence. Conversely, an act-only framework gives the model the ability to search external databases, but denies it an internal reasoning space. The agent blindly queries terms over and over. The blind querying fails because the model receives data but has no workspace to synthesize those observations into a coherent, forward-looking plan. It pulls the facts but cannot connect them. Pure internal thought hallucinates, and pure external action wanders aimlessly. Reliability requires a structure that interleaves logical deduction with direct observation, continuously correcting the trajectory. This log shows the REACT, or Reason plus Act, framework running the exact same query. It forces the model to generate a specific thought first, stating it needs to search for the Apple remote. It executes the search action and receives an external observation. Based on that text observation, the agent generates a second reasoning trace. It deduces that the remote was built for the front row media center and immediately initiates a new action to search for that specific software. The search fails, but because of the REACT loop, the agent analyzes the negative observation, recognizes the missing data, and refines its search parameter to include the word software to get a clean result. The accumulated observations provide the final puzzle piece. The agent synthesizes the data in its final thought sequence and outputs the verified answer, keyboard function keys. This Reason Act Observe framework scales directly to spatial tasks. In the AlfWorld simulation, an agent must find a pepper shaker and move it to a drawer. Before executing any movement commands, the agent generates explicit think steps. It deduces that a pepper shaker is most likely located on a countertop or in a cabinet, mapping out a logical search trajectory. As it moves, it runs a continuous update cycle. If it receives a state observation that a drawer is closed, it reasons about the obstacle and generates a new sub-action to open it before attempting to place the object. The REACT architecture forces the model into a strict cognitive rhythm. It translates static text predictions into a resilient, dynamic problem-solving loop. The evolution of dialogue systems began with the rigid, hard-coded keyword heuristics of early mainframes, where every conversational turn required a manually constructed rule. We bypassed that bottleneck by serializing state tracking into continuous text strings, eventually allowing models to pause generation and dynamically query external databases via API. The REACT cycle serves as the cognitive engine for these systems, bridging the gap between processing language and executing deliberate actions in an environment. Yet the core paradox remains. Despite navigating physical simulations and managing complex database queries, the underlying models are, at their core, still just calculating probabilities to predict the next word in a sequence. Meticulous prompt engineering and environmental feedback loops create this agency. By forcing the model to treat its own generated text as a workspace, we coordinate simple probability calculations into functional behavior. By strictly structuring the input sequence so the model is forced to show its logic, query reality, and observe the results, we have engineered a static language model into an autonomous agent.